Next on our agenda is Matt Davis. Matt is a director of R&D and applications here at Luna and has a deep reservoir of expertise and experience in the technology and in the application of fiber optic sensors in a wide range of applications, including, of course, testing and monitoring batteries. Matt will give us an overview of Luna's technologies and applications, focusing on fiber optic sensing. And I do want to remind everyone again, please do submit any questions you have for Matt using the Q&A widget in your Zoom console. We should, after Matt is finished presenting his presentation, we should have some time for some live Q&A. So please get those questions coming in. Okay, so with that, we'll turn it over to Matt.
Good morning, everyone, and welcome. Today, I am going to introduce Luna's technology and show some of what it's capable of surrounding making measurements and doing sensing in battery and battery-related applications. So at Luna in the Lightwave division, we focus on fiber optic sensing and providing measurement solutions to our customers that deliver data that's not necessarily able to be gained in other methods or using other sensors, other measurement technologies. And our focus is to integrate the fiber optic technology to provide these solutions. Fiber optic sensing addresses several key challenges, many of which are faced by our customers in the battery markets as well as other applications, whether it be composites, structural design and analysis, and model verification, which is one of the first ones to point out. Having a dense measurement capability like we're able to provide enables you to calibrate and align the boundary conditions of your FEA models to match the conditions that your test article or your device might be able to undergo. That also leads into advanced manufacturing. 3D printing is becoming more and more used in prototyping and in some of the initial production runs of parts. And using optical fiber, whether it's embedded into the part or to make measurements on the part once it's been fabricated, will let you pull important data like residual strain to make sure that the parameters of your part have been properly met. And then you can take that data, feed it back into your models, or use it to better improve the process you're using for the manufacturing technique. Process control is another area where having the real-time dense measurements of your part or of what you're trying to make or manufacture lets you adjust the control parameters on the fly. One of the ones that I'll show in a little bit is going to be surrounding if you're trying to weld two thermoplastic pieces together, say if you're making a casing for a battery. The ability to monitor the heat in the part prevents warping of that part and enables a good joint to be made so you have structural soundness. And then finally, in-service monitoring. Once you've built a structure or you've got a piece in service, having sensing either attached to it or embedded lets you perform structural health monitoring on the part through time, identify if any fatigue is beginning to occur, watch for any excessive vibration that's not supposed to be there, and then also provide some means for event detection and identifying if something is starting to go wrong before it does become a catastrophic failure. So fiber can be used in all of these, methods or to provide all of these advantages over top of other solutions that may be out there. So at Luna, we have two synergistic technologies. We've got fiber Bragg grading-based sensing through our Hyperion, and that's typically used where you have cases which require a fast measurement rate up to about 5 kilohertz. You want to space your sensors out over a long distance, whether it be multiple meters or kilometers. They're very easy to install, and the Hyperion is used for strain, temperature, acceleration, vibration monitoring, and also making pressure measurements. Targeting, primarily we'll see it in civil structures, security, and then also some applications in the aeromotive and aerospace and automotive markets. Our other technology is optical frequency domain reflectometry, or OFDR sensing. And this uses the inherent Rayleigh backscatter of the fiber. It's typically used in applications where your measurements are going to be made maybe at a slower speed, more or less quasi-static. It can do continuous sensing up to ranges of 50 meters per sensor, and it provides a measurement every millimeter or so along the fiber, which gives you a very high spatial resolution picture of what's going on within your part or for whatever test conditions it might happen to be under. These sensors are also very easy to apply. Again, it's very similar to what you would encounter if you were either putting down a foil gauge or setting up some other systems. Primarily for strain and temperature measurements, again on both small and large structures, and it's used also heavily in aerospace and automotive. And then we also do a little bit of work in the energy sector as well. So I'm going to start off by showing a comparison between the two systems. And what I've got here in this test article is a cantilever beam that has one of the high-definition Rayleigh backscatter sensors around the top, and then we've got one of the fiber Bragg gratings attached there on the bottom. There are two notches cut into the beam, and that's what you're seeing right here in the data. On the left is from the Odyssey, so the high-definition sensing system, and you can see where those two notches are. There are stress concentrations that have been created, and they're mirrored on both the left and the right-hand side of the graph because the test sensor runs along the top and the bottom, so you have it in tension and compression. What you saw a second ago was that where the fiber Bragg rating is located, the data on the right lines up very well, or the same as the magnitude of what we're seeing from high definition on the left. And as we go through and we cycle the beam, you can see the benefits of the high-speed fiber Bragg rating on the right versus the Odyssey being able to capture the lower speed measurements on the left. So that's how you can use the two sensors together if you're going to be, let's say, using the Odyssey for determining where you're going to need to monitor when your part is put into service, and then using the Hyperion to monitor it. And one example of that we've got is on the American Magic boat. So for this particular case, the Odyssey was used as part of the design refinement tools during some early testing, and then the Hyperion or fiber Bragg ratings were put in place so that real-time feedback could be obtained during sailing conditions. And that was all used to optimize the performance of the boat before the competition. So when we look at fiber optic sensing, and really sensing in general, it can be put into effectively three bins. You've got single point cases where you've got a channel that has a sensing element at the end of it. In our case, we talk about fiber. So for this, we have a Fabry-Perot element at the end, and every channel is to provide you one measurement. When you go into multi-point or quasi-distributed, in this case, you can put multiple sensors on a single channel. So for the case of, say, a Hyperion, where we're using fiber Bragg gratings, we can put 40 gratings or so along a fiber, spaced at whatever happens to be the most optimal for our test article, and it provides a single independent measurement at each one of those points on that channel. When we move to using distributed sensing and the OFDR method, now the entire length of fiber is the sensing element, and at each point that we've defined, we get an independent measurement. And these points are spaced at 0.65 millimeters in the highest resolution and 2.5 millimeters in the coarsest resolution. So even at 2.5 millimeters, you're getting a little bit over 500 measurements per meter. So it's a very, very spatially dense measurement system. And the way that it works is using the principle of the Rayleigh backscatter pattern that's just inherent to optical fiber. So we scan a laser across a preset wavelength range, we send the light down the fiber, and then this weak reflective pattern gets sent back, picked up by our instrument, and using a combination of the time and the frequency domains, we're able to isolate both where along the fiber we're at, and then what order of magnitude something is stimulating the fiber at that point. And typically we'll look for using it as a strain or a temperature. So if we see a hot spot along the fiber. It's going to cause this backscatter frequency to shift, and then that has a fairly linear correlation to the temperature. And that's how we're able to make the temperature, or the same occurs with strain. When the fiber is stretched to a certain point, that pattern will elongate, and we'll be able to correlate that shift to the amount of strain that's been applied to the test article. Where that comes in hand is really, as I've mentioned before, when you don't know exactly where something may be occurring on your test article. And one of the good cases that can demonstrate this is when you're looking at impact damage on, say, a carbon fiber composite or any composite. Composites aren't going to necessarily transfer strain the same way that their metallic counterparts might. So what we'll do is we can put the fiber in a very dense pattern like is shown here in the bottom left, and when that panel is damaged, whether it be from an impact or from cracking as a function of fatigue, we'll start to see a strain signal at that location on the fiber, pull out its magnitude, and then we can provide that data to determine if this part should still remain in service, or to try and enable engineers and analysts to come up with what might be happening in this case. One of the other advantages when we lay the fiber out in a pattern like this is we're effectively creating rosettes across the entire part. So that also enables us to evaluate the full strain state of the part. From a modeling and from a manufacturing and model validation perspective, especially with additive manufacturing, when we go and embed the fiber sensing into, let's say, a large part, we can monitor for the residual strains once that part cools down, as well as using it for process monitoring during the printing. And where this comes in is parts more and more are additive manufacturing is being used to prototype them in advance of making a production run. It's a much lower cost means of finding out how well the design is going to work. And when you are prototyping in that manner, you want to make sure that your additively manufactured part is going to perform the same way as your production part. So you're going to want to instrument it and make sure it has the same structural and thermal parameters. So in the case of like a battery casing or some type of an enclosure, maybe you're going to want to go ahead, you'll 3D print it, you'll get everything set up. Once you start doing your first testing, you're going to make sure that, one, it's going to be able to structurally perform the way you want it to, and then also have the same heat transfer parameters to get the heat out of the battery the way that it was designed to. So by using the fiber in this manner, we're able both to qualify the parts in their prototype stage and then also during prototype testing. I mentioned earlier I was going to go over one of the examples we've got when you're joining two pieces. And in a test that we've done, thermoplastics are becoming more widely accepted just due to the properties that they can be reheated multiple times without having to worry about damaging the polymer itself. We can, in this case, put a fiber in the bond line of these two parts that were being joined. And we were able to monitor what the temperature was within that bond line and use that as feedback control to, in this case, it was an induction welding head, in order to adjust the parameters so that we didn't overheat the part and cause any structural deformities, and also minimize the degree of stresses that were left inside of the part once the joining was done, but also ensured that a good joint was made. So while we might not put the fiber into every single production part that goes in, it is a good way of developing the parameters that are going to help to speed up your manufacturing time. And in this particular case, we were able to reduce the welding time by up to 50%, while also ensuring that it wasn't overheated or underheated to ensure that good bond. So those are a couple of just the generic applications for how the fiber can be applied to some different areas of the design development process. When we look at it specifically in relation to batteries and using it as an effective and efficient design tool, it's applicable at all levels. At the cell level, it can be used to evaluate the effects of different charge and discharge rates, what those will do with cell chemistry. As our keynote speaker had mentioned, cell chemistry is one area that has a very large focus right now, as folks are trying to combine the largest amount of energy density into the smallest space while also maintaining a high degree of safety. Fiber is inert in many chemical environments, and it's also non-conductive. So when you're performing the discharge and charge tests on cells, you're performing damaging tests, it's a very good system to set up so that you can fully qualify what's going on both internally and externally to the cell as it's undergoing testing. Then once you take those cells and you combine them into a module, now you've got to look at different things like cooling effectiveness. Are you going to be able to draw the heat out of the center cells so that they don't cause a problem or enter into a thermal runaway condition? So that's finding hot spots among the neighboring cells. Monitoring it, so if a cell does start to go bad, if there was a manufacturing defect at some point in time that causes one to be weaker than another, the ability to monitor every single cell in the module is going to let you identify that much earlier. And then finally going up to the larger, at a pack level, once you've assembled all of these modules into a battery that's going to be put into a car or some other device, you're going to want to make sure that all of the connections are robust. Putting fiber across the terminals, having it run through different areas, make sure the good contact has been made. Looking at thermal profiles. Again, looking at how we can get the heat out of either the center or the denser areas where the cells are so that we don't enter into an overheating, or also, including safety, but not, accelerating the life of the battery. And then finally, monitoring the entire structure for failure. Having the instrumentation throughout, if it undergoes any type of a potentially damaging event, we can identify if it started to crack or if it started to undergo something or experience something that's going to cause a problem later in that enclosure's life. There are two ways that we can integrate the fiber into batteries. The first is just to go directly onto the terminals. And for that, we would take one of our sensors. They're roughly 200 microns to half a millimeter in diameter. And we can place and attach this across the top of every terminal, like shown in the top right. And that will let us measure the temperature at all of those points, looking for connections, looking for hot spots, be held in place with either a putty or some type of a silicone glue, just something to keep it where we want it for the measurement. The second way that we've gone about it is using a pre-made pad. So what we'll do is we'll enclose the fiber in Kapton in such a pattern that's applicable to our pack or our module. And this ensures that the fiber can be repeatedly placed at the locations that we're most interested in, and still giving us full cell coverage. So this is something that we've done on several occasions for different customers, in which having the ability to repeatedly manufacture quickly and in the same orientations is beneficial. So the first example that I'm going to show is temperature. For this particular case, we've got the fiber inside of a Teflon jacket, and we're holding it down onto metal cylinders that simulate 6 different cells. And inside each one of these cells, or inside 3 of these cells, there are heaters that are controlled by the power button and those 3 switches. And what we're able to do is control the temperature of one of those cartridge heaters, again, simulating a battery since I can't be forcing batteries in the thermal runaway in my lab. So the box will be turned on, we power it up, and you can see as cell 1 is increasing, and then slowly its neighbors, cell 2 and cell 3, are also starting to heat up. One of the big advantages of the high-definition fiber measurement can be seen when we change how we look at the data. We can change this view, so now we're looking at every single point along the fiber. So what you're looking at is the section of fiber along the cell that we started heating, and we can identify if it's heating uniformly or if there's a hot spot that's starting to form at one particular part on the cell. So all of this is done with a single fiber connected to the data acquisition system. that can send this information back to the users or to the battery management system so that it can be used for fault monitoring and providing just an indication of the individual cell health. A second application is looking at swelling. So, if we attach the fiber to the batteries and watch them over time, as they begin to swell, they're going to strain the fiber. In this case, we've got a rubber cylinder that's simulating the swelling of the battery. And as we compress down on it, you can see the cylinder effectively expanding. One thing you can also see is how uniformly we're pressing down on that cylinder, so you can identify where along the cell it's been swelling. And that goes to doing lifetime studies of different cells and how they'll be behaving over time. And that brings us to a case that one of our customers has used the fiber sensing for, and that's doing aging studies of cells. And in this particular case, the researchers were motivated to develop a pneumatically controlled press that's going to simulate the stiffness and conditions that exist on the cell while it's in service, so that as they undergo different charge and discharge cycles, they can try and make sure that the cell is being tested under conditions that would be very similar to it being in service. In this particular case, they used the fiber sensing to make temperature measurements and ensure that the temperature was being distributed and that it was homogeneous throughout the surface of the cell. So this is just one of the examples of implementing this technology into a real-world application. And finally, looking at enclosure optimization. So composites offer a lightweight, robust system for enclosure design, especially in electric vehicles where weight is paramount, or minimizing weight is paramount. So as these composite enclosures are being designed and developed, as I showed a little while ago in some of our examples from, monitoring the processes to assemble these, monitoring the composites, either throughout their lifetime, looking for structural health monitoring, and identifying any damage. And then also from a thermal design perspective, you could take and integrate the fiber just in some different ways onto the casing, depending on what you were going after from a design perspective or a measurement perspective, and then use that to evaluate it during testing to ensure that your design is going to be as optimized as possible before it gets released. And then, finally, one other potential application that the technology may be able to be used in someday is optimizing charging. So as electric vehicles become more prevalent, you're going to want to take longer road trips. So battery life is going to be a set amount. You pull into your charging station. Is there a way that we could use the fiber sensing to monitor these cells and their temperature during charging in order to optimize the charge rate? So either go faster or slower based on the environmental conditions that might exist, or just the general performance of the battery. And this may become more important as batteries have been in service longer. And this is something else that we could use that would optimize battery life. If we could determine the optimal charge profiles and then more accurately monitor them during charging, could we use this to reduce the time at the charge station, as I mentioned, extending battery life, and then also determine which particular cells may be, coming to the end of their life, so that they can be replaced and the appropriate maintenance actions taken. So that's just one application that I see the technology being applicable to in the future. So in summary, I've tried to go over just a general overview of some of the sensing technologies related to fiber that Luna has to offer, point out some of the advantages of that technology with respect to its immunity to EMI, its ability to tolerate the harsh environments, and then also the fact that it's non-conductive, so it's inherently safe for these applications. And it really does allow materials and structures to be investigated and seen like they haven't been able to be before. from instrumenting a complex geometry and validating models to providing feedback control for manufacturing processes. There are just many applications they can take throughout the design cycle for battery and electric vehicle systems. So with that, I thank you all for your attention, and I open it up to any questions.
Hey, great. Thanks, Matt. That's a great overview and introduction to the technology and a really interesting survey of different applications in the application of the technology to batteries. Again, if you have questions for Matt, please submit them through the Q&A widget in the Zoom console, and we have time to get to a few of those. Okay, so we've got a couple coming in. This is a pretty interesting one. Someone submits a question that fiber optics for thermal mapping is pricey compared to K-type thermocouples. The question is, what is a typical ROI, or if I'd rephrase that, I guess, how would you look at the cost comparison between the two?
Yeah, so your typical thermocouple is going to run anywhere from $15 to $50, depending on what you're getting, what type, or especially when we're looking at K-type. A fiber sensor is only going to be on the order of about 150 to 200, depending how long it is. I can capture a measurement every millimeter on that piece of fiber. So it really comes down to how many K-types are you looking at instrumenting. Once you start passing 3 or 4, now the fiber is very cost competitive.
Okay.
And also advantage of giving you complete coverage of your battery. So you really are going to be able to get a lot more data out of it.
Yeah, very good. Thanks. Okay, let's see. Another question is, can this technology be used on a drive test to find hotspots?
Yes, most definitely. And we have done, efforts with customers in the past in which we've done some here at Luna as well, where we've driven the system in natural progression to instrument a battery during that drive test.
Okay, yep. It's a question about, you showed a couple applications embedding the sensors, in composite structures and so on. How does this sensor affect the structural properties when it's embedded, I guess, either in the composite or a 3D printed part?
So the fiber itself in those cases is only 165 microns in diameter. That's with the coating included. The coating is typically polyamide, which is very well adhered or miscible in a lot of those materials that are used for 3D printing or for composites. So it doesn't have any structural effect on the casings or any other pieces that it might be manufactured into.
All right, very good. We have a question. How do you see the challenges integrating this with existing systems?
Right now, I think it's going to depend a lot on what the goal of that system is. If it's cases where we're trying to emulate an existing thermocouple or temperature measurement system, we're working to get certain capabilities into our platforms that are going to enable that. And then it's going to be an effort in software, making sure the data that we're providing is able to be interpreted by that existing system so that it can use it to its best efficiency.
Okay, very good. Thanks. Another question here. How easy is it to instrument the battery and pull the fiber through the cells in my automotive application?
I think there too, it's going to depend a lot on the specific application that we're trying to integrate into. If it's the case where we're trying to measure the terminals, then before the module is sealed up or the casing is sealed up, it's real easy to go ahead and just have the fiber run back and forth across. And then, like I mentioned on one of the slides, we've got cases where we can prefabricate the fiber into a pattern in between 2 layers of Kapton, which are also naturally insulative. so that the integration process can go much faster.
Okay, very good. A couple questions about the measurement rate. So what are the measurement rates with the system, and I guess related to that, how can you measure dynamic phenomena like vibration?
So the system is not suited well for measuring vibration. Typically signals on the order of 10 to 15 hertz are going to be easily acquired using the system. I don't remember offhand what our transient measurement rate is, but I know the measuring a rise in temperature does happen faster than you would expect to see on standard thermocouples. I'm not sure. I haven't compared it to the fast response ones yet.
Okay. Yeah, and I'll point out also, you mentioned the FPG system as well. That's capable of more dynamic measurements, right?
Right. That's going to get us up in the 5 kilohertz range.
Right. Okay, very good. Let's see how, yeah, I guess you kind of, I think this is from the same person asking about the ROI and the cost of thermocouples. Yeah, let's move on. Can this scale to be portable? In other words, continue monitoring a car battery after it's been sold to the customer, so in operation.
So there are two ways you could go about that. I think the most effective means would be if you've got the sensor integrated into the battery and you'll periodically check it with a system that's not necessarily installed on the car, during, say, a charge cycle. So go see just how efficiently that battery is recharging. And in those cases, your model would be to have one system and then a sensor in each car. Another model could include if you did integrate the entire platform into the vehicle and watch it during the driving operation or during what the car's being used for. So I think both of those are possible. It just would come down to what's the most economical for the data you're trying to get from it.
Right. Okay. So can you reuse the temperature sensing fibers?
In most cases, you can. A lot of it's going to depend on what method you chose to integrate it into the battery or the test setup. If you've, let's say you're measuring cells and you're doing it non-destructively, so you're effectively wrapping the fiber around or placing it within, then at the end of the test, you just remove it and reuse it. If you get into cases where you're performing destructive testing or your integration method just isn't conducive to removing the sensor, they are fairly inexpensive. So I just go ahead and use a new one in that case.
Okay. So someone asked, can I press on my pouch cell with the fiber on it and view the temperature hotspots as I press to failure?
As long as the fiber's been placed appropriately onto that cell, you should be able to. If you're thinking about, say, a destructive test where you're going to be puncturing the cell, then you're going to see those hotspots very quickly. But we've done some testing in some different types of pouch configurations where we looked at the thermal profiles in between the layers of each of the pouches.
Right, very good. Yeah, in this question, again, you touched on this, basically a question about how costly are the fiber sensors compared to the number of thermocouples I would have to use to get the resolution that you have. I mean, it would have to be thousands of thermocouples, right?
Yeah, I believe at that point you present some safety concerns as well. The fiber it's not conductive. So, if we use even the coarsest resolution, every 2.5 millimeters, 500 thermocouples versus a meter of sensing fiber, the fiber would be very economical.
Yeah, absolutely. Very good. Okay. So I think with that, I think we answered most of the questions and probably should move on. Thanks again, Matt, for the presentation and for the Q&A. Really appreciate it.
All right. Thank you very much.